transport of mass. This is basically sometimes can be convection or diffusion, or momentum. Okay, this is basically flow. Well, actually convection is the same thing as flow. So mass transport is usually identified with diffusion process, okay, and energy. Okay, that would be like heat transfer. Okay, so momentum transfer is flow, mass transfer is diffusion, and energy transport is basically heat transfer. Okay, so mostly these three phenomena are involved in processes which we aim to be desired to model, right? Now, so they all follow different, uh, apparently different equations. Okay, their transport satisfy some equations, right? But actually speaking, they are all of the same nature, right? They can all be arrived by a very simple principle of balance, which is rate in minus rate out. So rate of accumulation is equal to rate in minus rate out plus rate of generation. This is the basic idea, and just if you mathematically elaborate upon these different terms, you get equations which would give you mass conservation equation, momentum balance equation, and energy balance equations. Okay, so let's see that. But before that, what do we get? For example, let's say if you have in general, if you have any property, let's say, and let's say any property which you call, I think yesterday we were doing that, but let me make it general. So generally, if you have any property psi, and this is, and you can define a small case psi as psi per unit volume. Okay. Then if you just look at this, so now we consider, for example, let's say one-dimensional transport, okay, property psi. Okay. So if there's a one-dimensional transport and you are basically trying to account for the property psi, so we consider a strip between x and x plus delta x. Okay. Now there will be a flux associated with psi at the two surfaces over here and here, and the flow is, let's say, the transport is happening in this direction. Okay, which is x-axis. Okay, so there will be a flux. Okay, so flux of psi, property psi, meaning psi cross the amount of psi, whatever the property, crossing per unit area per unit time. Okay, so amount of big psi, the big psi, okay, not a small psi, crossing unit area hello. When recording paused on me. Right. Thank you. I think I must have touched it by mistake. Thank you, Shivam. Thank you very much. Okay, I am sorry. Thank you, Shivam. So by mistake, I had paused. So all right. So maybe I can just, for the sake of recording, I'll just repeat whatever I just stated. So processes have, you are looking at the mass, momentum, and energy transport processes, and mathematical equation that we come up with for all these three cases separately actually can actually follow the same idea, which is rate of this conservation rule. Okay, and we look at when we apply the simple rule to different cases, what kind of equations we get, and something you can identify which you already learned earlier, right? So, for example, let's say, so we just talk about context with a general property psi, and then we'll apply to mass, momentum, and energy separately, right? So in general, any property psi, we can define a flux, which is amount of psi crossing unit area perpendicular to x-axis or flow direction, okay, per unit time. Okay. Okay. Now this flux will have invariably two components. Okay. One is called convective, and other would be diffusive. Where do these two components arise? Why do you need to consider these two separately? Well, this thing, this diffusive nature and convective nature separates out because of the fact that there's a graininess in the material. Okay? This separation, okay, but this difference of different kind of fluxes result. So this two different kinds of fluxes result from the graininess of the medium. Okay, so remember, at the molecular level, there you have empty spaces in between, right? So, but when you're looking at a particular region, for example, over here, you're kind of looking at average value. You're kind of smearing out that graininess. Okay. So if you look very closely, okay, so here you'll have different let's say it's water flow. You have molecules looking maybe like this under the very high strength microscope if you look at them. Okay, and because of this graininess, there will be their motion can be actually every each of these particles or whatever we call molecules will be having velocities, right? So their velocities would be rather flowing. There will be velocities that would be directed like this. So if you look at the overall motion, you may get a net velocity with which this bunch of molecules, which you identify as a fluid particle. Okay. So the fluid, you have a fluid particle, which will consist of maybe a millimole or mole, millimoles of atoms. Okay, they all would be flowing with certain average velocity. So it will be net velocity. That would be basically convection. Okay. But in addition, there would be a because of the graininess. Okay, they not all of them will be moving with the same velocity. There would be some of them would be deflected about the average velocity. Okay? So if overall velocity you found to be like this, some particles may be moving this way, some particles may be moving this way, some of them will be moving this way, some moving this way, and so on. But most of them, if you add it up vectorially, they'll add up and give you net velocity pointing in this direction. Okay. So what happens is because of this graininess, some of the particles may not be actually directed towards the 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 overall velocity direction, which is resulting into convection. Okay, and as a result, if you think of any cross-sectional area like this, okay, there will be a crossing that would be possible, even though overall particle is moving in this direction, but it's possible that the property may cross in this direction as well, okay, because of the graininess. Okay, So that leads to a different kind of transport called diffusive transport. Okay? So that diffusive flux. Okay, so that is what I am going to. There will be net overall average. Yeah, exactly. So yeah, so yes, yeah, absolutely. Yes, Anand, my answer to your question is yes. Yeah. So bulk convection would be basically, or macroscopic transport would be basically convection. And if you look at microscopic, because of the graininess, there is a spread possible in the velocity of these particles, which would lead to transport not occurring not necessarily in the convection direction, but in other directions as well. Okay, and there is a certain nature to that particular transport, because net velocity in these other directions is zero. Okay, there is no net velocity in other directions. Only velocity, only it exists in the direction, right? Other orthogonal directions, there are no net velocities. So, but there can be still a net transport in other orthogonal directions, which would arise because of diffusive motion, which is basically resulting from randomness in the velocities, which results from graininess in the medium. Okay, if there was no graininess, then you can think of like everything will have to be moving this way. Okay, but if you think like if you imagine there is grain, if you imagine like if you think of like a bunch of bricks connected end to end, and if you just shift one brick, the all brick will move in one direction without any if they are touching each other, if they're in each other, then all the bricks will move together. But if you just have a bunch of bricks which are not touching, there is a possibility of an individual brick to slightly sway away from the net motion. Okay, so that is what we mean by diffusive motion. Okay, Rohan, I'm coming to you. Just a second. Rohan, am I audible?
Yes, sir.
Yeah, tell me.
सर अगर पार्टिकल्स की मतलब अंदर ग्रेन्स की डायरेक्शन रैंडम रहेगी तो फिर पार्टिकल का फ्लूइड पार्टिकल का शेप तो मेंटेन नहीं रहेगा ना?
Of course,
क्योंकि
shape maintain बिल्कुल नहीं रहेगा. Of course, so that we have learnt already. Shape, when there is a flow, the shape is not maintained.
हाँ कंटिन्यूस शेयर तो रहेगा.
Yeah,
तो
yeah.
मतलब पार्टिकल अच्छा एक कोई इंस्टेंट पे देख सकते हैं ना मतलब.
Of course. Yeah.
ओके ठीक.
ठीक है. All right. Okay, so Amit, so diffusion is with concentration. Oh well, it is, but so yeah. The question is that there is a different question. Amit, your question is, it's so well. I'm not going to go into detail of that. We do that in the transport phenomena course, which we covered next semester. And it can be shown that if you just imagine, if you just consider this as a mechanism which is responsible for diffusion, then you will get that diffusion will result from concentration gradient. That you can mathematically show. Okay. So if this is the mechanism that I just stated, okay, and if you just use this mechanism and calculate the flux, it will result to be the flux to be resulting to be flux will. It can be shown that flux is directly proportional to concentration gradient. Of course, yes. So that is a mathematical. That's a manifestation of phenomena in terms of mathematics or physical quantities that we can measure. But what I just told you is basically where does it arise from? Okay, it arises from this simple mechanism. Okay, okay, but yeah, but you can consider this mechanism, and that will lead to diffusive flux, which is J. Let me call this D. In one dimension will be proportional to del C del X. Okay, and it's given by some kind of diffusion coefficient del C del X. Okay, where C is a concentration. Okay, so this is J diffusive in X direction. Okay, so this would be X direction. In general, if you have a motion, if you have probably if you consider three-dimensional case, then J will be a vector. Flux vector is given as D L C. Okay, So for now, just keep things simple and we'll just look at one-dimensional transport. Okay. All right. So there are two forms. One is diffusive, one is convective. Two forms of the fluxes, which we should be considering in general. Convective flux, now there's a very simple rule for finding out convective flux, which is convective flux is of any quantity at a point. Convective flux, which I think I've already done it in fluid mechanics class, but I'll repeat that. Convective flux of any property, okay, is basically given by the property capital psi is given by small psi, the corresponding psi into velocity vector at that point. That would be your convective flux. So that I'm going to call it Ga sub C. C stands for convection. So that you can check. So this is psi per unit volume. So this is basically the small capital psi. Small psi is big psi per unit volume. And this is length per unit time. That will give me psi per unit area per unit. Okay, so this is essentially psi per unit area per unit time, okay, which is a flux due to velocity vector. Okay, that means it's basically resulting from convection or net. Remember, this net that I'm measuring is basically the convection velocity, which is associated with the average velocity of the particles, which may be actually having slight randomness in the overall velocity distribution. Okay, all right. So you have two fluxes, convective and diffusive, and uh, convective and diffusive. Convective has a very simple form given by this. Diffusive will come to diffusive now. I already stated it here, so but I'll just write. Let's go back to our equation, which is rate of accumulation equal to rate in minus rate out plus rate generation. And we were looking at this particular scenario of one-dimensional case, right? So rate of accumulation would be del capital psi by del t. That is rate of accumulation. Now rate entering minus rate out. Rate in minus rate out. So rate in would be, again, I will be having two fluxes, Jc plus Jd. And we'll assume that they're only directed in x direction. So we'll not write component to x separately, specifically. Okay. We'll assume that this is one-dimensional. There is no other direction to worry about. So I will not write it in vector form. Jc plus Jd, okay, at x minus, well, so this is just a flux. I have to account for total quantity per unit area per unit time. So I have to multiply with and A times delta x. Okay, that would be the total volume. Okay, and minus, sorry, not delta x but area. So that would be, so this is per unit area per unit time. I have to look at per unit time that is crossing. I have to just multiply with the area that it's crossing. Okay, and then plus rate of, well, minus same thing, minus Jc plus Jd at x plus delta x into area plus rate of generation, which I'm going to write down plus psi g dot. This is the rate of generation. Okay. Now Jc I have already found out to be equal to small psi times v. Now I'm going to write this del psi. I'm looking at a volume which is not changing with time. Right? So psi can be written as psi times A times delta x del by del t. Okay, that would be equal to Jc is psi times v do A at x minus jc into a at x plus delta x. I'll just write again psi v a at x plus delta x. Okay. Again, same thing, jd into a at x minus jd into a at x plus delta x plus psi g dot. Okay. Now, we know that here, by our design, area is constant. We assume that its area is really constant. Area is constant. So I can take ax and ax plus delta x are the same. I can take this outside, and I'll have quantity psi v at x minus psi v at x plus delta x. To the first approximation in the limit delta equal to 0, I can expand it like del by del x of psi v into delta x, okay, with a minus sign. Okay, because you all remember what the definition of del f by del x is: fx f of x plus delta x minus f of x over delta x. Just use that and you'll get this relationship. Okay. In the same manner, plus a into minus del jd by del x into delta x. Okay. Now, and then of course plus psi g dot. Okay. Now I can here side delta x and a are constant. They're not dependent on time, so I can take them out. And on right hand side, I'll cancel a delta x with the right hand side. So you can also define psi g dot per unit volume actually. So that you can define a quantity psi g dot. I'm going to call. So let me call. Well, to start with, I should have probably multiplied with delta v rate of generation and okay. So I'll have delta v multiplied here and delta v multiplied here. So that when I divide by a delta x both sides, right? First of all, what I do is I take this out and I have this appearing on over here, and a delta x cancels out. Okay, over here and this and delta v. So I'll have these terms cancelling out. Okay, so that would give me del small psi by del t, okay, which is the concentration of the property psi. Now, property big psi, this is per unit volume. This psi is concentration of psi. Okay, that would be given by del x of psi, okay, with a minus sign. So what I can do is I can instead take it on the left hand side. So conventionally, it's written like this, okay, equals to minus del A diffusion by del x plus psi g dot. Okay. All right. Now, so and remember, v is the bulk velocity or convection velocity. Convection velocity. Now comes the constitutive relationship, which is expressed for JD. Okay, so generally JD, as I told you, as what Amir, the question that was asked by Amir, is JD is related to concentration gradient. Okay? In general, you can write it as a property. So JD, you can show that if you just consider that particular mechanism, simple mechanism of how that flux arises because of the graviness in the medium, okay, and the randomness in the velocity. So that will lead you to the following result, which is JD is proportional to del psi by del x. Okay, the gradient inside. All right, and that is going to this all the constant of proportionality. Let's give it a general name, del psi. So this so that is what we can utilize here with a minus sign. So the positive side decrease next direction. Okay, GD will be directed towards positive x. Psi decreases in the positive x. Okay, that's like negative concentration value. So, well, if you interpret psi to be number, big psi to be a number, okay, then small psi becomes a concentration. Okay, and this becomes concentration gradient. This becomes mass flux or number flux. Okay. All right. So, but in general, this can be identified with other cases as well, not necessarily mass, but momentum and energy as well. So, okay. So the now this would be that would give us del by del x into delta del psi by del x. Okay. So this would be basically your constitutive relationship that defines one of the material properties, delta. Okay, this is material property. And this will have different meaning in context of different size. For example, as I told you just now, if you take psi to be the capital psi, the big psi to be mass, then this is nothing but a diffusion coefficient. You'll see that if you take this to be momentum, then this will be actually a kinematic viscosity. Okay, we'll see that. All right, so, and then plus psi g dot. Okay, so basically what we have arrived at is the following equation: del psi by del t plus del by del x of psi v equals to so one dimensional will be complete transport. Going to the generation term first, and then plus del by del x delta del psi del x. Okay, so now let's just look at this this relationship in context to different quantities psi, right? So as I showed you, this is basically flux, diffusive flux. So now let me just write down different cases. So now if you consider so quantity psi being transported, quantity being transported, okay, associated flux, okay, and delta. So we'll just write down, I'll just write down for different cases. For example, if it's mass, okay, then the flux is this delta, the mass flux is called J. So this is mass flux, okay. Or if you're looking at a mole, you can express the same mass in terms of mole of a species, then that will be molar flux, okay. So this is that's represented by J, okay. If you are momentum, okay, momentum is m times v. Let's consider one dimension, so I've not put a vector sign over here. So so now momentum in general, I should probably bring momentum the last. Energy first. Energy, and that is associated flux is heat flux, which is generally written with Q. So this is heat flux. Okay, so energy crossing an area per unit time per unit area. Okay, due to diffusive motion. Okay, so this I'm looking at a diffusive flux actually. Okay, so not conductive flux but a diffusive flux. That is nothing but the heat flux. Okay, so energy that is transported from one part of the material to the other part across a surface, which is caused by randomness in the nothing but energy heat flux. Okay, that is what we are going to call Q. Okay, and momentum associated with momentum. If you consider psi to be momentum, then what is this flux? What does so momentum transported or crossing? Now remember, momentum is a vector. In general, momentum is a vector. Okay? So, for example, if you have, let's imagine you had this, okay, and you set in motion the molecules on this side, okay, fluid. This is like entire. This is like one particle, and it consists of lots of molecules which will have some intermediate space. So when you set this fluid in motion, not all of them actually will be moving. So let's say you give the velocity in this direction. Some of them will be moving this way, some of them will move this way. Most of them will be moving somewhat in this direction, but maybe slightly dispersed about this particular direction because they are allowed to they have space available around them so that they can actually just wiggle around. Okay, so that is the kind of velocity distribution you will get on the molecular level. Okay. Now because of this, it may so happen that if you look across this surface, this molecule, let's for example, will cross the surface. Okay, may not be exactly directed in this direction. And as it crosses, it may hit the molecule which is over here. Okay, and it will impart a momentum in this direction. Okay, so in general, there can be a momentum transfer. Momentum transfer is nothing but hitting someone else, okay, and imparting your momentum to someone else. Okay, it's like exerting a force onto something, right? So momentum putted across this surface, which is like force experienced by this part due to this part, okay, would have, in general, need not be in this direction. It can have components in this direction and this direction. All right. So therefore, momentum, due to this greeniness, the momentum transported per unit time per unit area across this surface can have actually three independent components. One could be parallel to the velocity direction, and two would be perpendicular to the uh, velocity direction. Okay, just a second. Hello, hello. अरे अब्राहम क्या हुआ? नहीं, मैंने तो नहीं लिया, वही रखा होगा. अच्छा, मैं आके ढूंढ देता हूँ, मैं आके ढूंढता हूँ. हाँ, ओके, ओके, बाय बाय. Sorry, that was the sound. So, anyways, how is this relationship? There's a question with respect to Reynolds transport theorem. Actually, it's the same thing. Well, Reynolds transport, yeah. So Reynolds transport theorem, you can. Well, actually, Reynolds transport theorem is also nothing but you're right. So it's nothing but the it's nothing but the accounting. Okay, it's actually balance equation only. Only thing is that Reynolds transport theorem, the treatment is more mathematical. Here it's more physical. Okay, because you start with accounting, rate in minus rate out equals to plus rate generation is rate of accumulation. That makes that so when I do fluid mechanics, I assume that we are not chemical engineers, we are general engineers. Okay, but when I'm chemical engineering related course. So I start with this engineering perspective, and that's. But actually, you're right. So this is the same thing. You still get the same relationship. You're right. Thank you, Alok. Okay. Anything else? Can we say the same for material oil derivative? Well, actually, if you look at this, well, if you, since you brought it up, if you look at this term, okay, this term is nothing but d psi dt. That is material derivative, which is given by del t plus v dot del, which in this case becomes v into del, v del by del x psi. Okay, so this is nothing but material derivative. So yeah, so yeah, so this is material derivative. I think is that a question? Is that what you want to ask? Hello? I mean, left hand side, what I have here in this balance equation is nothing but a material derivative. And if you, so yeah, okay. Now, what you can imagine, you can also imagine the same problem by, so well, maybe since you brought it up, maybe I can just point it out here also. You can imagine now, imagine small volume. What I imagined right now was it's like in the constant fixed volume in space, right? But you can imagine that you have identified this bunch of particles and you move with that. Okay? When you move with that, okay, and then account for the rate of change of, then basically apply rate in minus rate out equals to rate of generation plus rate of accumulation. Okay, if you do that, if you're moving with the particle, then this will become your rate of accumulation, which is d psi dt, and there will be no convective flux because since you're moving with the bunch of particles, nothing, there are no new particles entering or leaving. Okay, there will be no convective flux, only diffusive flux would be possible. So that would be given by this term, and generation could be possible. So that would give me this term. Okay, so if you think of this in terms of Lagrangian derivative or Lagrangian picture, then you can imagine that you're moving with this set of particles so that convective flux crossing the boundary is zero because you know new particles are actually overall entering. But there could be diffusive flux, which could be basically moving away from this. So that part would be this one. But anyway, let's not get into that. Let's just stick to our this picture. Okay. All right. Okay, let's continue then. Now, so momentum transport will be basically associated with two kinds of, or actually three different components of forces would be experienced due to momentum transport, diffusive momentum transport. Okay, so diffusive momentum transport leads to one component. Well, let me get this. Cross a surface, okay, will lead to a force parallel to the motion, that is convective motion, motion, okay, and two components Well, actually, I should say, well, one component would be perpendicular to the surface, and two so maybe I should write like this. I should need to force parallel to the surface, and perpendicular to the surface. So, force parallel to Ajay, just a second. The surface and sorry, we should say perpendicular here. Perpendicular to the surface and two components parallel to the surface. And what are those? Basically, that's momentum crossed per unit time and per unit area. That's momentum flux, which is nothing but this force per unit area, which is nothing but stress. So basically, you're going to get for any surface, you're going to get three stress components. One would be perpendicular, which is called normal stress, and two would be the parallel ones, okay, which would be the shear stresses, right? So in general, when there is a diffusive momentum transport, that leads to generation of normal stress and two shear stresses, okay? So this diffusive flux is nothing but normal and shear stresses. Normal and shear stresses. And depending on which way you choose your, we have already seen that, which way you choose your surface, if you generate 9 independent quantum numbers, so you will have sigma ij matrix. So sigma is basically diffusive flux for momentum. Momentum diffusive flux is the same thing as stress tensor. Okay? That is what is the there's a correspondence between of the different terms. So that's all. Okay, so now let me come to the question. First of all, someone raised a hand. Let me go back to the Ajay. Just a second. Ajay, you had raised a hand. I guess your answer is no. See questions. No. There would be one perpendicular, two parallel. No, we are so here we am looking at. So I'm not. No, here in general you are looking at a surface, right? So this is a surface, and um, the surface has two parallel directions and one perpendicular direction, right? So across a surface, the momentum would be transported, momentum will be transferred, or force will be exerted, which may have component parallel to the surface and perpendicular to the surface. Perpendicular to the surface, if you consider outside as positive, then it has only one direction, and perpendicular can be broken into two directions. So that's why I'm calling it two perpendicular, two parallel, and one perpendicular. That's all. Okay. It doesn't have to do with any 1D motion or doesn't have to do with 1D motion. In 1D motion, um, if you have one-dimensional motion, we'll come to that. But what I'm talking here is for a general case. Okay? Because I wrote MV as a vector here. Right? So if I consider this to be a vector, which means that momentum can have any direction, or flow can be in any particular direction, not necessarily one dimension. Then you will generate normal and shear stresses, right? No, yeah, exactly. I'm sorry. So probably I mentioned it wrong the first time. I said parallel to the flow. You're absolutely right. So yeah, forget the parallel to the flow. We are talking in parallel to the surface, not the flow. Okay. Sorry about that. I had probably caused a confusion. But this parallelism is not with respect to flow, but with respect to surface that we have identified. Absolutely. Right. Okay, any more questions? So now, all right, so let's proceed then. So these would be the fluxes. If you can consider different quantities as mass, momentum, and energy, the fluxes, corresponding fluxes which we identify, which is given to be this quantity. Okay, so this is the diffusive fluxes for different types of transport are nothing but this is mass flux, energy. If you think this to be energy transport, there is heat flux, and momentum transport is correspond to momentum transport, momentum flux, which is nothing but stresses, right? And the corresponding J's would be, so for J here, so here what you say is, now this would correspond, the meaning of delta would be associated with the corresponding constitutive relationship, right? So in case of mass, you say J is proportional to del C del X, and you write J equals to D del A by del X, the minus sign, of course. Okay, so that D would be delta. Okay? This D is nothing but delta. Okay, consider psi as mass. Okay? In case of energy, if you recall, the heat flux is proportional to temperature. You recall the Fourier's law. Okay? So heat flux across a surface, okay, Q is proportional to alpha delta del X. You recall Fourier law. Okay, so that would be identified with delta here. Okay, and momentum, if you recall, del, so del sigma by del, let me just write this. This is a little tricky, but you can identify rho momentum transport will be given by shear stresses. And if you recall, shear stresses were given by sigma ij was mu del vi by del xj plus del vj by del xi. Okay, and for let's say here in one-dimensional case, that would be basically only one of this will survive. You will have only mu del Vx by del y or something. So if V is only directed along x direction, Vy is 0, you will get del Vx by del y. So sigma xy would be equal to del Vx, mu del Vx by del y. Okay. So in that case, it's much simpler. Okay. So in that case, it's much simpler. Okay. So that mu has to be identified. This mu has to be identified with this delta. Okay. All right. So maybe I have to see the factor. Just check. Should be yeah, that's right. That's right. All right. So you see that. So basically, idea is to identify the same balanced equation results into different kind of equations. So now let's write down for each case. Now, having identified the corresponding uh, deltas, first of all, we identified what is the quantity. Then we identified what is the diffusive flux, what quantity, physically, what this diffusive flux of that particular quantity represents. Okay. And then knowing the constitutive relationship for each fluxes, we identified what is the physical interpretation of deltas when you consider different properties psi, right? So that is what we have just achieved here. So, but the bottom line is that all these three different equations actually result from the single balance, the single philosophy of balancing out things. That's all. Okay. Okay. Now let's now further elaborate upon just plug in these expressions for different quantities. So let's say I choose psi to be mass. Okay, so I have mass balance equation, okay, which is basically also called continuity equation. Okay, and here what do I do? So I define a quantity. So let's call mass is related to total mass. So I'm going to rather write, since we are actually from a chemical engineering perspective, I'm going to write down not mass of a particular species, but number of moles of a particular species. Okay, psi, big psi can choose to be, let's say, number of moles of species, certain species, right? Number of moles of species. Okay. So L, so that therefore let's call that species A. So the concentration of that species is then Ca by del T plus L by del X Ca times V. Okay, Vx actually. That would be equal to so here I'm going to call rate of generation of A as RA per unit volume. This is rate of generation of A molecules per unit volume. And then plus del by del X d del Ca by dx. Okay, so that would be our mass conservation equation. What we saw in the fluid mechanics class was if you consider, so remember in fluid mechanics class what we saw was a special case of this general relationship. In fluid mechanics class I had only one species. Okay? One species, I mean single fluid flow. Okay, we did not consider presence, whatever fluid I had, I considered it to be one single species. I was not bothered about different kinds of species. So Vx will be the same as the net fluid velocity. And if you look at this quantity, so del by del X Ca times Vx. Okay, so that would be equal to Ca del Vx by del X plus Vx del Ca by del X. Okay, so this quantity will be 0 because I know del dot V for the net fluid, the carrier fluid, overall fluid, del dot V equal to 0 from the incompressibility. And what we obtained was, and right hand side, in the fluid mechanics course, we did not consider uh, reactions, right? So the fluid overall is not changing; it's not being generated. Anyway, net rate of generation of a fluid is mass is anyway 0. Okay, so if you think of the overall fluid, Ra would be 0. There'll be no diffusion. So right hand side was 0, and as a result, we obtained the formula that is del rho by del T plus uh, V V dot del rho. That was 0. Okay, so this is what we have obtained for incompressibility. Incompressibility. So in general, del rho by del T plus del dot rho V equal to 0. This is what was in general for compressible or incompressible. So this would be compressible or incompressible. Okay, so in that case, that's what completely physical phenomena, which is flow of a single phase, single component fluid, and right hand side would turn out to be 0, no reaction, no diffusion, whereas generally the flows involve reaction and species basically they chemically transform from one kind to the other kind. Okay, and they can also that will lead to concentration gradients, and that will lead to diffusion. So diffusion will be important. So this is the most general form of mass balance equation in a flow system which may be possibly undergoing reactions. Okay. All right. Okay. So, and of course, this would be species wise mass balance, species wise, and there will be overall mass balance which will be given by this. This will be basically overall. Okay. So that is about mass balance. Now let's look at the energy balance or momentum balance, maybe. The next one, energy balance. Again, this will give us a equation. Hold on, I didn't finish this one actually. There's further this. Now there's a further simplification that's possible. Is you can actually assume that if you assume diffusivity to be constant, okay, that will give me this term to be, this would be equal to, so diffusive term will be given by d del square Ca by del square. Okay, so that's one of the very important equations in modeling a flow system. Okay, all right. So that would be further reduced. And rate of reaction, for this you have to do kinetic study. Okay, so that's where chemical reaction engineering comes into picture. So rate of reaction, you can study the kinetics of a reaction. You can study separately how, if you have a particular under certain conditions, physical conditions, how fast a particular, remember what is this rate of generation of A molecules per unit volume, right? So this would be basically equal to rate of change of concentration. Okay, if you fix the number, fix the total volume, this would be the same as rate of change of concentration. And that you can separately study and come up with the kinetics laws, okay, which you can use over here in flow systems, right? So you can do the batch process. Okay, you can take same kind of species maintained under same set of conditions like temperature, pressure, etc. Okay, same kind of solvent, and look at how fast the concentration changes. You can come up with the expression that would model the rate of the rate of generation of A under the set of given conditions. Okay, that you can plug in over here. That is obtained separately from kinetic studies. Okay, so this is obtained from kinetic study. Okay, all right. So basically, so having done this, now what you have here is what are my unknowns? My unknowns basically two things: the velocity and concentration. Okay, so that has to be solved. Okay, okay. Velocity can be actually independently be achieved by solving fluid mechanics. So if you can solve from fluid mechanics and find Vx, then you can actually plug in this over here and find how the concentration at any point and at any time will change. Okay, will change with x and t. Okay, all right. Next, we were talking about energy balance, right? Let's quickly write this down. So here I'm going to identify psi, small psi, would be nothing but I'm going to talk about thermal energy. Okay. So that would be rho Cp into T. Okay. Because mCpt would be the total energy, so content, with assuming that T equal to 0 is fixed to be my zero energy value, the reference energy value. So small psi will be given by rho Cpt, and as a result, I'll get the equation that would look like del by del T rho Cpt plus del dotted with rho Cp T into V is equal to psi g dot plus del dotted with alpha del rho Cp T. Okay, so this would be your model equation. Heat generation, rate of generation of heat. How does that come into picture? How do you account for that? Well, for example, if there are reactions occurring, there could be exothermic or endothermic. That would lead to non-zero term. So that's where this. So from a reaction kinetics and its energetic study, you can find out whether as the liquid flows, does it chemically transform and result into loss of energy, or basically it absorbs energy. Okay, accordingly, your psi g dot will result. Or for example, if there's a nuclear reaction going on, it may lead to energy generation. So anything of this kind may lead to generation of energy. All right. So that would be your energy balance equation, and of course, a momentum balance equation is something that we have already seen before, which is nothing but momentum balance in flow. Okay, flow systems, that will give me del by del t. Okay, and here that would become mv. Okay, that would become rho v plus del by del s rho v. Okay, you all remember about this notation? Well, I'm not going to elaborate upon that. Please check your notes. Then I'll have rate of generation. Okay, so here psi g dot, okay, plus sigma ij, a diffusive flux, right? So sigma, well, so that. So del by del dot sigma, right? So this should be del sigma. Correct, del sigma. Del sigma. Okay. Okay, so this is a form, and generation of what? Momentum. Momentum, where what generates momentum? Well, external force generates momentum. So here we will look at what external forces might be acting. We will have a pressure force, and gravity. Okay, so okay, so that would be basically, remember, this is also a force, nothing else than that, nothing other than that. But we have but this is like a dissipative force, or basically this is coming from the diffusive kind of motion, which is basically shear forces, okay, resulting from diffusive transfer of momentum. Shear force or shear stress. Okay, it's actually shear force per unit volume. Okay, and this would be associated with pressure wave and gravity. These are the two forces acting. Therefore, that would lead to, this would lead to, I'm not going to detail of that. This would lead to minus del P term, and this would lead to rho G H term or something like that. Right? So that would be actually lead to the generation, which is actually which is like acting up, which is like the element that we're looking at is being acted upon from external forces, which are basically from the pressure at this ends and gravity, which is due to Earth. Okay, so those external forces will lead to generation of momentum that would be accounted for in this term, and diffusive transport would lead to shear forces, that would be a counted system. Okay, and that's how you get a momentum balance equation, and you can check that this is something that we have obtained already in our fluid mechanics class. All right, so that would be your momentum balance equation. Yeah. Navier-Stokes, well, Navier-Stokes it becomes Navier-Stokes when you next apply how do you express sigma in terms of mu, right? So you write for linear fluids, sigma mu del Vi by del Xj plus del Vj by del Xi. Substitute this, then it becomes Navier-Stokes equation. Absolutely. Right. NR equation. So did you mean NS equation or NR equation? I think I assumed that you meant NS, right? Navier-Stokes. So yeah. So in this itself is not called Navier-Stokes. Remember, Navier-Stokes equation applies to linear or actually Newtonian fluids. So you have to apply, you have to assume how liquid responds to applied stress in order to call it a Navier-Stokes. So if the stress is proportional to gamma, okay, so when sigma is proportional to gamma dot, that is Newtonian fluids. And for Newtonian fluids, yeah, Rohan, I'm sorry, you have 11:30 class. Okay, okay. I'm well past my time limit. I'm sorry about that. So I'll stop the class and we'll meet Monday. All right. Any question, you can just let me know. I'm going to stop the class. Rohan, I'm very, very sorry. I completely missed track of time. All right, any questions? Okay, then I'll stop the class and until Monday.